Thank you very much for joining us here for this second part after the coffee break. I hope you again had some very interesting discussions. And we continue this session with Thomas Nowotny from the University of Sussex. Thank you.
Thank you very much. Yeah, welcome everyone. I want to talk today about how we are trying to scale up training with event prop, which allows you to calculate exact gradients in spiking neural networks, to problems that go beyond proof of concept type of benchmarks, like MNIST and the yin-yang data set. So to start us off, I'm just going to make a brief introduction what this is all about. So we're going to talk about spiking neural networks that are defined by leaky integrated fire neurons and current-based synapses, like so, where you have a leak integration is an ordinary differential equation. Then if you pass a threshold, you emit spikes. That then means that a weight-dependent current is added to the postsynaptic neurons, and these currents decay exponentially, which is the second differential equation there. And then what we do with it, for the purpose of this talk, is classification. So we stick this into a network, and let's say we wanted to classify one of those MNIST digits, the number 2 there. We turn that into a spike pattern. So these dots there are supposed to be spikes. And that's this time, and this is the input channel, so to speak, the input neurons. We stick that spike pattern into our input layer of input neurons, and then from there on out, it's the system of differential equations I was talking about for a hidden layer and for an output layer. And here the output neurons are non-spiking, and we classify based on which of the neurons is the most active. So in this case, I made it a little bit different color. So we look at the output voltages, and whichever has the highest voltage, that's the decision of the network. How would we then train this thing? And for the purpose of today, we're going to do gradient descent. And I made a very simple picture here that everyone will have seen in a textbook before, where gradient descent is like descending on a loss landscape to the deepest point, where a suitable chosen loss function is at its minimum. And then the loss function is supposed to measure how well the network does. If it's at this minimum, it is its best, and then we get the trained network from that. In order to do so, we calculate the gradient, just shown here, and then we update the weights with a learning rate proportional to that gradient, which corresponds to going down the steepest way on that landscape. And while this is a very simple picture, I hope it will, in a moment, explain why we had some trouble scaling up this learning to harder problems that I can then show in pictures in addition to the formula. Now, I said I wanted to talk about event prop. Event prop now is this method where we can calculate the exact gradient of a spiking neural network of the type I was just introducing. And while this might look a bit daunting, don't be afraid if you don't get every detail of this. What's important here for the purposes of this talk is simply that we can define a loss function, and if it's of this shape, then we can use the event prop formalism. So it can either be a function of the spike times, here called t post, or it can be an integral over a trial, 0 to t, of a function of the voltages. And that's what I'm going to use here for these non-spiking output neurons. And then the nice property of event prop is that on the forward pass, it's the leaky integrated fire neuron I just introduced. And then there is a backward pass with so-called adjoint variables, which has the exact same shape as the forward pass. So we still have ODEs, and they're exactly the same type of ODEs. And then the loss function comes into this partial derivative there, dLV dV. And then we have this kind of ugly formula here, just ignore them for today. Those are the events that then transport errors back from later layers to earlier layers, and they look a bit more involved, but it's not that important now. What makes me excited about is that then you get the gradient directly from these lambda I variables, and overall you have a system where you have just some ODEs to integrate, and then you have these conditions when jumps occur, spikes occur, and on the backward pass you have the same structure, ODEs plus some jump conditions. We have developed software for this in computational neuroscience for about a decade now. Ours is called GeNN, GPU-enhanced neural networks, and this software can simulate this kind of equations very, very efficiently. which means we already have the tool ready now to simulate this, because that's what we were after for the whole time we were doing this. But because EventProp has the same shape backwards, we also have very efficient code for learning. So with this, I went on and say, okay, let's just quickly reproduce what was in the original EventProp paper. And we implemented the so-called yin-yang classification task, and we reproduced the results. I did the MNIST, latency encoded, bit like I showed in the introduction. That worked perfectly fine, and it was really fast. Yeah, so we could train MNIST in 15 epochs to about 97% correctness on the test set, and it just takes about 29 seconds, the entire training. So that was very promising. So I thought, oh, we're to a brilliant start. Now scaling up will be really easy, and we're going to just solve all these more complicated problems. And I decided to work on this one, the so-called spiking Heidelberg digits. They came out in 2021, were made in Heidelberg, where people were recording the spoken digits. So people went to a sound studio and they were repeating 0, 1, 2, 3, 4, and so on. And in German as well, 0, 1, 2, 3, 4, 5. The recordings were taken, put through a cochlear model, and then turned into these kind of spike patterns. And this is again, x-axis here is time, and then the y-axis is the input neurons, the channels if you want. And it looks a little bit like a spectrogram, which is what you would expect. And the task now is to recognize from these spatial temporal spike patterns which was the spoken digit and in which language. So there's 20 classes here. And I implemented it, not a big problem. I ran it, and the system learned with EventProp absolutely nothing. Chance performance, and it wouldn't work at all. And in the next slide, I will try to explain to you why that is. Unfortunately, this is a fairly involved problem, so bear with me a minute or two while I try to explain it here. The learning between the hidden layer and the output layer works just fine, so I'm not going to talk about it. So I'm going to talk about here what happens here, learning the weights from input to hidden layer, which presumably should be optimizing the representation of information somehow in the hidden layer. Now, if we start learning and we use, for the purposes of this, I started with this loss function. So this has the shape that's required for EventProp. You have a function of the voltages here, and you integrate over the trial time. And this is like a typical cross-entropy loss, where L of I is the correct label, and these are all other labels. So you can easily see that, that this loss function will give you a high value if the correct voltage is not high enough and it's low compared to the others, and if it's high compared to the others, the loss function goes towards 0. Now, if you start training, of course, the network doesn't know anything, and it will make mistakes. And then your loss will typically look like I've drawn here by hand, obviously. It's non-zero already at the beginning when no one spikes. So now that's when all the voltages, output voltages are 0. That's not good classification, right? It's not the right voltage being high versus the others. So it's already a non-zero loss. But then if the wrong voltages go up and the right one goes down, it gets even worse when the spikes occur. So here's the input digit for reference. Yeah, so when there are no inputs, it's already bad. Then it gets worse, and then it gets bad again, but not 0. Okay, and now when I explain the rest of this, it's important to realize that because it's calculating exact gradients that depend on spike times, following the gradient with EventProp will not do anything about creating extra new spikes or deleting them. That information is not included there, right? It's only about when do the spikes occur and how does that change the loss, and how does the change in the weights change that timing and therefore the loss. Okay. So what we need to discuss now is what happens if we look at one spike here in one of these hidden neurons, and what would happen if it was earlier or later. So let's say it was later. Then if this neuron had an output weight onto the correct output neuron that was positive, then it could decrease the loss here if it was a bit later, right? Because it's here higher loss than there, so it could really decrease the loss. if it happened a bit earlier, it could decrease the loss here, but there's not so much to be gained here. And this is important to realize, I mean, this is a saturating function, right? So there's a diminishing return when you're closer to 0, so you can achieve more here. So that means when I follow the gradient here and I do all the calculations, what event prop will tell me is to decrease the weight towards this this hidden neuron that made that spike. Which will make the spike later, and then it has a bitter effect on the loss. And if I have a neuron, if the neuron happened to have an output weight that's negative, then with the same type of argument, it makes the loss worse, but it makes it a lot worse here and a little worse there. So the spike would be moved forward. That means the weight is increased onto this output neuron if it has this hidden neuron, if it has this effect on the output. So this means, and this is already kind of showing where the problem lies, this means that the neurons that are useful, making useful spikes that excite the neuron that should be excited, they are gradually turned off because the input weights are diminished to move the spikes backward. And the ones that do the wrong thing, they suppress the output neuron that should be high voltage, they are being moved forward, and therefore they get higher weights, and they get increased activity. And this leads eventually to deleting the spikes in neurons that are useful and increasing spiking in neurons that are not useful. And I could show directly, among other evidence, that this is what was happening. And so here I was just training one single output 0 and did that for a while, and then I examined the weights onto the output neuron 0, oops, and I ordered the neurons by that. And the ones that, this is the average number of spikes that these neurons were making for inputs of the type 0. And you can see the ones that have positive weights on the correct output neuron weren't actually spiking, and the ones that are spiking have negative weights. So it learned the opposite in the hidden layer than in the output layer, and that obviously couldn't work. Yeah, in a sense, what was happening was we were falling down the gradient, and that was great. But then at some point we lost the spike and we jumped back up, and so we ratcheted up the gradient landscape instead of going it down, because we deleted the spikes that were the most useful to decrease the gradient. Now what's the solution to this? Well, instead of looking at a loss function like this, we need to remove this artificial drive of moving spikes around in the hidden layer in an unhelpful way. And to do that, we can just move the drive, remove it totally. So now I swapped here the integral with the cross-entropy term, and I'm taking the cross-entropy of the average voltage. In the average voltage, it doesn't matter where the spikes occur, and therefore now I have almost no gradient in the input hidden layer. That kind of works, but it is very slow in learning, obviously, because there's no gradient in the hidden layer. But then I introduced an artificial weighting term, which reintroduces a gradient. And if we go through the argument again, and for the matter of time I wanted to do it, if we went through the argument again, you could see that this weighting term now introduces the opposite force, where the right spikes are enforced and the wrong ones are deleted. Okay? And then in terms of pictures, it's a little bit like having this situation and turning it into this one, where you see the difference here, it curves up and drives you away from the spike deletion problem. And with this, I could now successfully learn this task, and then achieve the performance that was at the level that was originally achieved with surrogate gradient descent on the spiking Heidelberg digits. But in the meantime, everyone else has been busy, and they have improved with all kinds of other mechanisms to show that they could do even better with surrogate gradient descent. And so I felt I had to kind of catch up. And for the last 1.5 years, since that original result, I've been throwing the sink at it in terms of other ways of improving the network. And lo and behold, you can achieve state-of-the-art performance with event prop. And I'm calling it state-of-the-art here because most of the other people, as I show in red or in brown, they're using the test set here, so it's a bit hard to tell what state-of-the-art exactly is. But I'm claiming that with a 93.5%, I'm roughly there. If I also did that, this gray one up here that I purposefully made invisible would be 95.5, so we're in there. And now last thing, what actually helped doing this in this big list of things that I flashed at you. It was just a few particular augmentations on the input data that helped us get to that type of performance. So you see this brown, gray, and purple are the highest performers here. Now I'm out of time, so I go straight to the summary. And I would formulate it like this. Yeah, we take event prop, we add this loss shaping where you avoid the problem of the spike deletion and creation that was unhelpful, plus all the augmentations, and you can get state-of-the-art with exact gradients. So thank you very much for your attention.
Thank you for this very short but very informative talk. Are there any questions here? And I guess by now you know the game. There are 4 microphones, so please just come forward and ask your question. And don't tell me you're tired. We just had a coffee break, so no excuses. Let's see, 2 people are moving. Yes!
I got there first. Hello, my name is Mark van Rossum, University of Nottingham. Can you comment more about the role of recurrence? Did you need it in the end, or it was just a bit of extra boost you got?
Yeah, thank you very much. So it went under in the rush a little bit, but what I found is that the recurrent networks, and you saw the 2 diagrams, left and right of the original result, the recurrent networks were to the right, they were always better, no matter what loss function, than the feed-forward ones, and substantially better. So without recurrency, I don't get anywhere close to the state-of-the-art. So it's very important.
Thank you.
Hi, Jan Finkbeiner from Research Center Jülich. This loss shaping you're talking about, could this also be useful in the case of surrogate gradients or similar methods?
In principle, I mean, I have no evidence, but in principle, it could be. With the surrogate gradients, the situation is slightly different. So with the surrogate gradients, if I can just say it very roughly, you have more extra information that the spike might soon be deleted because you're kind of smearing out the signal around the spike, so to speak. Yeah, so this is very hand-wavy, I'm aware, but one can go through the math a bit more carefully, then you can see while you're learning and you're going towards the point where you actually lose the spike, there's a signal that the loss is getting worse. So you kind of have this up-curving edge already automatically, more or less. But it could be that that's not strong enough and you're still losing the wrong spikes. In that case, it would be helpful also to shape the loss. It could also improve the learning speed. I saw that this, what I called the beneficial drive, the weighting in the loss function, it made learning a lot faster because the gradients were much stronger now in the hidden layer, and the kind of flow of gradients across layers was better.
Great, thanks.
One more question?
Jimmy from Zurich. I was wondering, like, it's just a follow-up of Jan's question. Did you try just embedding an activity regularizer?
So I have suppressed that information in the talk, but all of this is on the background that I have a regularizer in place on the hidden layer. The problem was with the original loss function, the regularizer didn't save us because it was equally trying to kind of reinstate spikes on all neurons, not specifically on the ones I was losing them on. Right? So this balance still went wrong, even though overall I kept the spiking level okay. Right? So it wasn't the problem of a silent layer, which you would normally get. Yeah? I had solved that with a regularizer, but the regularizer couldn't help that the wrong neurons were doing the wrong thing, right? That the hidden neurons were doing the opposite of what the output weights were learning.
Thank you.
Thank you. Any more questions? Then let's just say thank you again to Thomas.
Thank you very much.